Now let us take a body which has holes in it. So um, these holes are C1, C2, Cn, etc. And we call a generic hole Ck. Okay, this is what we are going to work on. And C1, C2, every hole has a set of loads that are specified on it. So this is X1 and this is y1. These are the loads that are applied on the boundary of the hole. Each hole is subjected to a load of this kind. So this is xn, yn. These loads may not be point loads. These loads don't have to be point loads. These are the loads that you get if you integrate the tractions that are applied on the whole boundary of the hole. Now, because this is a multiply connected body, we want the potentials to be analytic in this region S, which excludes these holes. So we can now afford to have functions that are not analytic all over the plane, but can have poles at isolated points z1, z2, zk, zn, etc., which lie inside the holes. So it is possible to have functions that have singularities, poles at isolated points inside the holes, which means that remember your complex variable theory that we recapitulated two classes ago, last week. So remember that now if we take a contour which goes around the whole boundary, we take a contour which goes around the whole boundary in this direction, then this contour integral will be 2 pi I times the residue inside the contour. So uh, this contour integral will not be zero, because we have allowed the functions to be non-analytic at points inside the hole. So if you take a contour integral, then it will be equal to 2 pi I times something, which we have to calculate. Now we also have done quite a few problems where we have shown that taking a contour around the whole boundary, is equivalent to taking any other contour that does not exactly match the whole boundary but goes all the way around the hole. Why? Because of the Cauchy integral theorem. Remember, in the yellow part, the function is analytic. So if I take a contour now which goes like 1, 1 to 2, 2 to 3, 3 to 4, then I have taken a cut that joins to the outer boundary C0. So 4 to 5, and then goes round and comes back to 7 and then back to 1. So in this contour, which is this yellow contour here, yellow region here, in this region the function is analytic. So everywhere inside this contour 1, 2, 3, 4, 5, 6, 7, the function is analytic, and therefore its contour integral over this whole contour 1 to 7 has to be equal to 0 by Cauchy integral theorem. But then we will use this usual trick. We will call this function not fz, but we will call it f prime z. Doesn't matter, f prime z is an analytic function. We just call it f prime z in hindsight, because it will sort of simplify things a little bit. So if I take the contour integral over 1, 2, 3, 4, 5, 6, 7, I obviously get 0. Now this contour is composed of contour over 1, 2, 3, 4. So 1, 2, 3, 4. The contour over 5, 4, 4, 5 and 7, 1 are traversed in opposite directions, and they're basically virtually touching each other. So those two cancel out. And then we also have the contour over 5, 6, 7, which is actually the contour over CK traversed in the opposite direction. So the contour integral over 5, 6, 7 is negative of the contour integral over ck. So what we have is the contour over the outer boundary 1, 2, 3, 4 is equal to negative of the contour over 5, 6, 7, and this negative is actually the contour over ck. So the contour over ck, contour integral over ck, is same as contour over 1, 2, 3, 4, which is an arbitrary curve around the hole. Arbitrary curve 1, 2, 3, 4 is an arbitrary counterclockwise contour around the hole. So what we have proved is contours over ck are contour integrals over ck give the same value as any other contour around the hole taken in the counterclockwise direction. So that's what we have proved, and now we will have to choose a function f prime z which uh, gives me some value of this. So this, let's say over the kth contour, let this integral, the result of this integral, be alpha k. So what kind of a function should f prime z be, so that if you take a contour integral around the hole, any contour around the hole, you would always get alpha k. So there are many candidates for this. We already know that if I take uh, if I take fz to be equal to log z, for example, log z minus zk, log z minus zk, uh, when integrated over a contour, we have already done this, integrated over the contour ck, this will give me 2 pi I. This will always give me 2 pi I, and I need alpha k. So if I take alpha k divided by 2 pi I, so this is 2 pi I. So if I take alpha k divided by 2 pi I times log z minus zk over ck, then I am sure that when I integrate this, I'll get 2 pi I, 2 pi I cancels, and the result will be alpha k. So this is a possible choice for fz, which means that this is a possible choice for f prime z. So f prime z will be 1 by z minus zk alpha k 2 pi I. On top of this, I can have a function f star added to fz. Just for the sake of generality, I can have a function f star added to fz. F star is a function that is analytic everywhere in the plane. Even within the holes, it's analytic. You can have a function like this. Why? Because when you integrate over ck, this function will give you 0. So this arbitrary function can be and indeed should be added to fz to make it general. But this is the trick term. This is the term that ensures that when you take a contour over every hole, when you take a contour over around every hole, you get alpha 1, alpha 2, alpha 3, up to alpha n if there are n holes. So fz is taken as a summation of all these terms, each giving you alpha n, uh, alpha k when integrated around the kth hole. Similarly, f prime z will be of this form. If fz is of this form, and you will have f star prime z, which is again analytic because f star is analytic. Okay, f star, remember, is analytic everywhere, so it's most likely to be a polynomial kind of a function. It is analytic everywhere except um, yeah, except nothing, sorry. So it's analytic everywhere. Okay, now armed with this idea, let us take our capital omega z and small omega z in this form. So we just take a constant. So suitable functions for a body with a hole are going to take this form. The form is going to be some constant, which is what was alpha by 2 pi I in the previous slide. This would give you the residue when you go around the whole k, and then you have analytic function which is analytic everywhere. Similarly, for small omega z, the constants are different, the analytic function is different, but the form is the same. And this is the analytic, these are the analytic functions, analytic potentials that you will use as Km potentials. Again, the constants gamma k and beta k will be determined from boundary conditions, and we'll see how that is done. Okay, so what are the boundary conditions? In this case, we have one given boundary condition when we know that the total load over each hole, uh, in particular the kth hole, is xk plus iyk, and we have an expression for the total load. If you remember, for the total load, if fs is the total load, we have ifs is equal to um, capital omega z plus z omega. So this is over from S1 to S2, where S1 and S2 are the same. S1 and S2 are is the integral around this whole. So if you take an integral of this, function, you should get I times xk plus iyk. So that is what the, uh, the boundary condition is on each hole, and we are going to use that in order to determine the alpha case and the beta case that we have chosen. Okay, so we also have the displacements. So the displacement functions, remember, are similar. Displacements are similar. So you have 2 mu d is equal to kappa times the same thing. I think there's a minus. This is minus 4 nu minus 3 minus z. So this is the displacement, and if you are given the displacements at some point, then you can use this function. But we are going to use both of this. This we know, this is equal to xk plus iyk on the kth hole. This we know, and this we are going to use to make some useful assumptions about alpha k and beta k, and then we are going to use this one to finally find alpha k and beta k in terms of the forces that are applied on each hole. So let us take the displacement first, and if you take the displacement and you write down um, the various terms. So omega z is, capital omega z is this, and then omega z prime will be uh, gamma k by z minus zk. So this would be, and this would be bars of this, and then you have small omega z, which is this, and small omega z bar will be beta k bar log. Now take this and plug it into the displacement equation, and that is what we have done. This is the displacement equation, and this is minus of 4 nu minus 3, so we have written it as 3 minus 4 nu. This is your omega z. This whole thing is your omega, capital omega z. Then this is your this whole thing is z times omega prime z bar, and this whole thing is your small omega z bar. Okay. Now, the multi-valuedness of uh, D. D is now a multi-valued function because of these terms. These two terms. These are multi-valued functions, we know. These two are multi-valued functions. And in particular, their imaginary parts are multi-valued. Remember, log z was log r plus I n 2 pi I n theta. So the imaginary part is multi-valued. So the imaginary part has to be this equation has to be such that gamma k and beta k have to be such that the imaginary parts of this term and this term go to 0. So that is what we have written. So the imaginary part of this whole term, which is this, and the imaginary part of this whole term, which is this, they have to be equal to 0. And this can be shown to be true if this equation is equal to 0. And with the above connections, we now have expression between gamma k and beta k, which will allow us to eliminate one in favor of the other. So we have eliminated beta k. From this we find that beta k is equal to minus kappa gamma k. That's kappa is equal to 3 minus 4 nu. So this is equal to kappa. So using this kappa, we can now eliminate one of the two constants. So we have only one to determine. So gamma k is the only one to one constant, one set of constants that we have to determine, and we have come to that from the fact that d has to be d has to be a single valued function, and all multiple valuedness from the right hand side has to be removed, and that can be removed only if minus kappa gamma k is equal to beta k. So that's what is the first step. The second step is to now use the boundary condition that we are given. So on ck, on any uh, of the holes, this is the load. So I had IFS equal to, so I've taken the I've multiplied both sides by I, and then you get a minus I on the right hand side, and this is the total load, Fs. This is what I had called Fs. So I had IFS, I've multiplied by I and taken the I to the other side, is equal to this quantity evaluated over Ck. This quantity evaluated over Ck over a closed contour Ck. Now evaluating it over Ck, we know, is equivalent to evaluating over any counterclockwise contour that goes around the kth hole, right? And of this you will see that this quantity and this quantity contain log z terms. This quantity here contains z by z bar minus z bar k term. So this quantity has prime here. So prime of capital omega z is 1 by z minus zk, and this function when integrated over ck gives you 0. So this function integrated over ck will give you 0. You can easily verify that. Take z minus zk. To do this, take uh, z minus zk equal to some other function u, and then z is equal to u plus zk. Zk is a constant. So using these substitutions, you can easily prove and take this to be equal to r e to the power I theta, right? And then dz equal to r e to the power I theta I d theta. So using this, you can calculate this integral from theta equal to 0 to 2 pi, and you will see that this integral is equal to 0. So this does not have any contribution from this contour integral. This and this have contributions, but we know the contributions already. This contains the logarithmic term. So the logarithmic term, if you go back, so if you integrate this over ck dz, so this integral will be 0 because this is a function that is analytic everywhere. That's how we have chosen it. This integral would be equal to 2 pi I, and you have the gamma k. This integral again will be 2 pi I, and you have the gamma k. But we have already shown from the single valuedness of the displacement that, this will be beta k. We have already shown that beta k is equal to minus kappa gamma k. So this quantity would be minus kappa gamma k 2 pi I. And this again dz of this over the whole thing would be equal to 0. So we already know what these integrals are, and that is what we are going to put. This integral will be 0, this contour integral will be 0, this will be beta k times 2 pi I, this will be alpha k times 2 pi I. Use the relationship between beta and alpha, and this is what you will get. So you will get that gamma k is equal to xk plus iyk divided by minus 2 pi 1 plus kappa, and we put that in to both the equations, and these are the final set of um, potentials that we get inside this contour C naught. So remember, we took a contour which encloses all the holes in the body, and inside we started with the assumption that we can now afford to have a function that is analytic only in the yellow part but can have poles inside the holes. So with that assumption, we came to the conclusion that this function can be of the form log z minus zk over every hole. So this is a function that uh, would exactly give me 2 pi I when I integrate it over each hole, and then we can have an arbitrary analytic function, analytic everywhere function um, added to it. So with this, we assumed capital omega and small omega, and then use the single valuedness of the displacement to reduce the two sets of constants, alpha k and beta k, gamma k and beta k, to one set of constants, and then use the fact that each hole has a total load of xk plus iyk applied on it. We found the constants exactly, and these are the results. This is the result of those functions inside the domain C naught. This is what we did. Now, let us do a small uh, modification to this. Not exactly a modification, small extension of this. Let us try to find what this function, what kind of form this function is going to take if we evaluate it over a contour C which is far away from all the holes. So C naught is enclosed inside C naught encloses all the holes, and earlier we were trying to find the function maybe somewhere here, close to the holes. Now we are looking at points which lie on this C which is far away from the holes. So what we are asking, how should the potentials be as I go far away from the holes? One thing is certain: the total load on this C is going to be the sum of the loads on each of the holes. That follows from a free body diagram. So the total load on this should be sum of xk plus iyk, where this goes from 1 to n. So this should be the total load that acts on C. And again, I can have I need to have a function that has poles inside C, that can have poles inside C, but in the blue region, or in the bluish gray region, if you take a point Z here, it should be analytic at this point. But it can have, and it does have, singularities inside C naught. So that is the kind of function we are looking at. and that kind of function would be log z. So the origin lies inside C naught, and that kind of function would be log z, because log z integrated over C, log z integrated over C would give you 2 pi I, right? It will always give you 2 pi I, and we can use that uh, along with the fact that the total load on C, will be equal to summation of the loads on each of the holes. So uh, these are again analytic functions which are analytic everywhere, that can be added, because if you take integrals of this over C, then this should be C not C naught. Okay. So this is the form of the function. These are the forms of the function far away from the holes, and this is the form of the function in the region close to the holes. Okay, the functions are essentially the same, except that far away from the holes, zk is small compared to z. All the zk's are small compared to z, so these reduce to log z. Far away from the holes, these reduce to log z, because zk's are small compared to mod zk is small compared to mod z, and that is the reason why you have functions of this form far away from the holes. As you go away from the holes, these z minus zk's all reduce to log z. The constant remains the same, except that now you have the total summation of the loads here. Uh, earlier you had uh, this this summation here. Okay. Um, this you have because now on this contour C, the total load is equal to the sum of all the loads applied on the holes. So that is why the total load is, I have called that x plus iy. And this is the form of the functions away from the holes. Now these are analytic functions. And these are analytic in this annulus, in the gray annulus. This annulus, they are analytic. And we know that functions which are analytic in an annulus, it is analytic here, functions which are analytic in an annulus can be expressed as Lorentz series. So I can express these functions as Lorentz series, and this is how I do it. So Lorentz series, remember, contains all the negative and positive powers. So these go from minus infinity to infinity. So I have these unknown constants, and these are the Lorentz series form that these analytic functions are going to take. Now, if we need that these go to zero as mod z tends to infinity. So if these have to go to zero, then these can contain only the negative powers and not the positive powers. So this is the form of the function. So we have to delete the positive powers from it. So this is the form of the analytic function that we can have, and these are the uh, potentials that we have very far away from the hole, and they contain only these negative powers of z, and they also contain log z. So with this, armed with this, we can now solve a problem. Um, just one point, we can have what about the z equal to n equal to 0 term. The n equal to 0 term will give you a constant, and we drop it because that constant will never enter the stresses, so we don't really need it, and we can, without any loss of generality, we can take that to be equal to 0. So that's what we have done. We have not retained it. We have retained terms from n equal to 1 to infinity, where this series is in terms of z to the power minus n. So remember this, and now we will apply this to a sort of simpler problem. So the simple problem is something that you might have done in your elasticity courses. This is an infinite plate with a circular hole of radius a, subjected to a set of remote loads. I'll not solve this problem till the end, so I'll leave a few last final steps to you, but I will start you off. So what we are now going to do is the following. What we are now going to do is the following. Uh, we are going to apply these set of equations. Immediately what we see is there is no load on the hole. So this is equal to 0. This is equal to 0. And therefore I have only this term and this term left. So that is what we are going to do. And yeah, so I retain this and this. What is this? Remember, when we looked at these equations, we said that, well, these are Lorentz series, and we should get rid of all the positive powers of z, because they go to infinity as mod z tends to infinity. So we cannot have them. We need these terms to go to 0 if mod z goes to 0. So we had taken all the positive terms of this list, and we retained only the negative terms. That was based on the premise that these guys have to go to 0 as mod z tends to 0. However, in this case, they don't have to go to 0, but they have to go to these constant values that you have specified far away from the hole. These constant values that you have specified. So far away from the hole, somewhere here probably, you should have potential functions that lead to these stresses. And we have already done this problem for infinite plate. Yes, here we have seen that the potentials will take this form, where they have to go to sigma xx infinity, yy infinity, and xy infinity at the remote boundary. So this would be the form of the potentials as you go very far away from the hole, and the effect of the hole will be taken care of by these terms. So these terms take care of the effect of the hole. So the effect of the hole does not have the log term in this case, because the hole is unloaded, and therefore these are the forms of your potentials. How do you determine an and bn? Of course, you determine them from the boundary conditions, and so the boundary condition is on r equal to a, sigma rr plus I sigma r theta has to be equal to 0. So apply the km equation in polar coordinates now, and in polar coordinates, sigma xx, sigma rr plus sigma theta theta is equal to 2 omega omega prime plus omega prime bar. So this is the first equation. The second equation is sigma rr minus sigma theta theta plus 2I sigma r theta equal to minus 2 z omega double prime plus small omega prime. This is the form. So on the boundary you have sigma rr plus I sigma r theta. So add these two. This cancels out, and then you have 2 sigma rr. You have 2 sigma rr plus I sigma r theta is equal to, you have 2 I theta here. You have this in the polar coordinates, you have this 2 I theta. So this will be equal to The 2 will cancel from both sides, so let's not write the 2. We have omega prime, and this you will have on r equal to a, and this has to be equal to 0 because the traction conditions tell you that this is equal to 0. Where does it come from? Remember, the traction is 0, so Tr is 0, T theta is 0. Tr is sigma Rr Nr plus sigma R theta N theta, but the normal in the in the polar coordinates has Nr equal to -1 and N theta equal to 0. That's the normal. So for this whole, the normal is this. So this normal in r theta coordinate will be minus er. So its components are -1, 0 in the cylindrical polar coordinates. So this is, so Tr is 0, which means sigma Rr is equal to 0. Similarly, T theta will have minus sigma R theta, and this is 0, which means sigma R theta is also equal to 0, and that is what I have written here. That is what I have written here, and that translates to this in terms of the potentials. So now I have the potentials, I have the boundary condition. I'm going to plug this into this and then try to find out these unknown constants. Okay, so this is what we have done. On r equal to a, we will one by one evaluate each of these functions. So omega prime z, you can do the evaluations yourself. So this will contain powers of minus n plus 1 I. This will be plus n plus 1 I. This will be plus n plus 1 I, and this will contain um, n minus 1 I. So now these are the four terms that contain these summations. So we take them to one side. So this, and so this whole sum is equal to 0. The whole sum is equal to 0, but we keep these known terms on the left. So these are known terms on the left, and these series terms on the right. Now we are going to say that, okay, what powers of e to the power I theta can we have? So we can have e to the power minus 2 I theta, and we can have e to the power 0. So e to the power 0 is here, e to the power minus 2 I theta is here. So the summation goes from 1 to infinity. So 0 can only result from this term. For when n equal to 1, you will have b1 divided by a square, that is the radius square, e to the power 0. So that has to be equal to, if you equate the same terms, that has to be equal to sigma xx0 plus sigma yy0 divided by 2. So this term has to match with this term 1. 2 minus 2 I theta can come when n equal to 1 here, but it can also come when n equal to 3 here. When n equal to 3, you can get no sorry so when n equal to 1, you will get minus 2 I theta here, but in the process you will get plus 2 I theta here, you will get plus 2 I theta here. This you will get for n equal to 1. When n equal to 1, this will give you e to the power I0. So this is, we have already taken care of this here. Now this, so what it means is that again when n equal to 3, this term will give you 3b3 by a to the power 4 e to the power 2 I theta. 2 I theta cannot occur in any other term. It will occur for the A terms for n equal to 1 here and here. It will occur for the B terms for n equal to 3. So that will be this term. And minus 2 I theta can occur only with the A terms when uh, n equal to 1. That is going to come from here. So when n equal to 1, this guy has to be equal to this. On top of that, this term for n equal to 1, this term for n equal to 1, and this term for n equal to 3 has to go to 0. The sum of these three terms has to go to 0 because there are no powers of plus 2 I theta on the left hand side. So doing that, we come to the conclusion that B1 is directly obtained from the 0 term, A1 is directly obtained from n equal to 1 term, and then demanding that the powers of plus 2 I theta go to 0, we need to have this equation as well. So we need to have B3 in terms of A1. So A1 we already know, and B3 therefore is easily obtained. Okay. Now for the simpler case, when only sigma yy0 is applied, so there is only tension that is applied. That's a problem that's done in elasticity courses, not by using this method of complex variables, but by other methods. And in those cases, if you plug in A1, B1, B3, etc., these are the final forms of the potentials, Km potentials that you will get. Now, what I leave for you is use these equations to find the stresses, and then compare the stresses with what you have got from elasticity. In particular, if you remember that the elasticity solution told you that at the equator, at these points, the stresses that you get on the surface of the, so this stress that you get on the surface of the hole is 3 times the sigma yy naught that you have applied. So 3 times sigma yy naught is what you will get here and here. Especially this relation you should verify with the stresses that you get from these equations. So take these equations, plug it into the stress equations, find the stresses, and just make sure that you get the same solution as you get it from elasticity. So we'll show one more example where we will use arguments of this sort to come up with potential functions. And that is the case of a half plane. So we want to determine the most general form of the solution very far away from these holes. This half plane has holes. So now this is a half plane problem. This side doesn't exist. So on the half plane problem, we have taken a contour that is very far away from these holes, and we want to figure out what this function is going to be. Obviously, just like in the full plane problem, we can take the functions to have this form, log z form, because log z we know is going to give us 2 pi I if I integrate it over around the origin. And these are very far away from the holes, so log z is fine. We have to determine gamma 1 and gamma 2. In order to determine gamma 1 and gamma 2, what we are going to say is we are going to evaluate the load on this contour. We are going to evaluate the load on this contour, the total load on this contour. And to do that, let us take 2 points. So let us take this angle alpha. So this angle is pi minus alpha, and this angle is alpha. So ZA is RA e to the power I pi minus alpha. ZB is RB e to the power I alpha. So these two we are going to evaluate it from B to A, and so we are going to evaluate this quantity, I times this whole quantity from B to A. And that is going to give us the total force on the arc C. So once you do that, this is what you will get. It's easy to do. You plug in this ZA into log, you calculate log ZA would be log RA plus I pi minus alpha. Yeah, this is log ZA. Similarly, log ZB equal to log RB plus I alpha. So log ZA would, so gamma 1 times log ZA would give you omega, and small omega would be given by log gamma 2. Doing that, plugging it into here, you get this expression. Figure it out. Now, to cover the whole half plane, I need to make alpha go to 0. So if alpha tends to 0, alpha tending to 0, this line falls on this line falls on this line, and therefore I cover the whole half plane too. So if I make alpha go to 0 here, then this term goes to 0, and this term also goes to 0. Okay. Now, this total force will be, so this log RB by RA term cannot be here in this expression. The reason for that is I am trying to figure out what is the form of the potentials very far away from the holes. That means as mod Z tends to infinity, which means that both RA and RB tends to infinity. When RA by RA and RB both tend to infinity, log RB by RA is not defined, is infinity by infinity. That's something that is not defined, and therefore I cannot have this term in this expression. So which means that gamma 1 plus gamma 2 bar has to be equal to 0, because this term cannot be there. This term cannot be there. Then I take alpha to be alpha to tend towards 0. So then with this condition and the fact that this whole thing is equal to P, which is the total load on the curve, I get the simple expression that P is equal to 2 gamma 1 pi. Okay, and then gamma 1 and gamma 2 bar, the sum is equal to 0. So once I know gamma 1, I know gamma 2 as well, and with that I have now found the constants gamma 1 and gamma 2, and I plug them in, and these in terms of the loads, and this is the form far away from the holes in a half plane. In a full plane with holes, far away from the holes, the form is here. The form is this. Okay, far away from the holes, the form is this. Close to the holes, the forms are these in a full plane. In a half plane, these are the forms of the potential far away from the holes as mod Z tends to infinity. So as you see, these are some of the problems that we can quickly solve with with the techniques that we have learned, especially with the Kolosov-Mushkelishvili equations. And now we will take up some problems which will take us closer to what we want to do, that is solve the stress fields for cracked bodies.